Swayam Prabha. Digital India. Educated India.
Welcome to the third lecture of the lecture series on tutorials on design of transmission elements. This third lecture is on tutorials on design of helical gears. So let's start with a brief description about the helical gear. As we know, helical gears are used to transmit power between two parallel shafts, but their teeth are inclined to the axis of rotation by an angle which is called the helix angle. The problem is a 7.75 kilowatt electric motor runs at 30 rps revolution per second in a clockwise direction as viewed from the positive x-axis. That means when it is viewed from the positive x-axis, it is rotating in a clockwise direction. Key to the motor shaft is the 18 teeth helical pinion. To this motor, the helical pinion is keyed and it has number of teeth equal to 18, and the normal pressure angle is 20 degree and the helix angle is 30 degree and a normal module of 2 mm. Now, we have to find reaction at bearings A and B of the pinion shaft, and thrust should be taken out by the bearing at A. We know that in the case of helical gear, an axial force also acts at the point of contact or the pitch point, and so an axial component of the force will also be there at this point. So this A should take care of that axial force. So here the bearing will be radial plus thrust. We know that in the case of helical gear, the teeth are inclined by an angle equal to helix angle psi, and when the teeth are viewed in the tangential direction and in the normal direction, AA is the tangential direction and BB, when we take section along this BB, then it is the normal direction. Then the gear teeth will view like this one in the section BB, which is the normal, and the pressure angle corresponding to that view is called the normal pressure angle, and the pressure angle corresponding to this AA view, AA section, is the tangential pressure angle phi t. In the problem, normal pressure angle was given, and so with the help of normal pressure angle and the helix angle psi, we can find the tangential pressure angle phi t, and that is given by tan inverse tan of the phi n divided by cos of the phi. Substituting the value of phi n and psi, we get phi t, that means tangential pressure angle 22.8 degree. Now, the pitch circle diameter of the pinion can be determined with the help of the module in the transverse direction. When we see the gear in the AA section, which is the transverse direction, then the module will be called the tangential module MT, and when it is viewed in the section BB, then the module is the normal module MN. With the help of normal module MN, which is given in the problem as 2 mm, and the helix angle given as 30 degree, we can find the tangential module, which is 2 divided by cos 30 degree, and thus the tangential module is 2.309 mm. Now, pitch circle diameter of the helical gears are determined with the help of this tangential module, not with the help of the normal module. So, with the help of this tangential module, we can find the pitch circle diameter of the pinion, which is number of teeth multiplied by the transverse module MT, and it comes as 41.562. Now, knowing the pitch circle diameter and the revolution of the pinion shaft, which is 30 revolution per second, we can find the pitch line velocity at the pitch point of the pinion, and that will be pi dp np divided by, actually it will be, when this is in rps, revolution per second, and dp is in mm, then it will be divided by 1000 to make it in meter per second, and it is divided by 1000, and so the pitch line velocity is obtained as 3.918. Now, relationship between angles and component of the forces, cos of the psi is equal to tan of the phi n divided by tan of the phi t. The forces which acts, that means when a pinion is transmitting power to a gear, then the forces which are transmitted along the pressure line will have 3 components, and the total force which is acting is W, and its components are determined with the help of this normal pressure angle and the helix angle, and the Wt, the transmitted component which is acting along this, that means in the direction of x, when it is in the direction of x, and the value of that is given by Wn, the normal component of the force, cos phi n and sin phi. And this Wt is determined knowing the power which you want to transmit and the pitch line velocity which we had just determined, which is 3.918 meter per second, and the power are willing to transmit from pinion to gear is 0.75 kilowatt. So, 0.75 divided by 3.918 is 0.191 kilonewton, and that is the transmitted load Wt. Knowing the Wt, we can find the Wn, the normal force which is to be transmitted, and then the Wn is obtained as, knowing this Wt and cos phi n cos psi, it is this one. Then the radial component of this Wn is this one, and this radial component is Wn sine of the phi n. Substituting the value of Wn in terms of Wt, we get the radial force is equal to Wt tan of the phi n. Substituting the value of Wt just determined, and tan of the phi n is 20 degree and tan phi n is 0.42, and thus the radial component of force is 80.22 Newton. The axial component of force along the axis, Z is the axis. So, the axial component of force, this Wa is given by Wt of the tan of the phi n, and so substituting the value of Wt and phi n in this equation, we got the value of Wa, the axial component of force, which is 110.27 Newton. And thus, we have obtained in our problem, when the pinion was transmitting power to the gear, then what amount of tangential force, radial force and axial force will act at the pitch point. But the directions are not yet known. So, let us find the direction of the tangential force, axial force and radial force which will act at the pitch point. This is the pitch point. So, the transmitted force, the direction is determined from the direction of rotation of that particular driving gear. So, here the pinion is the driver in our problem. Therefore, this pinion is the driver, it is coupled to the motor and it is getting power, and so it is the driving gear. So, when it is a driving gear, then the tangential force acts in the direction opposite to its rotation. Now, when in the problem it was given that when we are viewing the pinion from the positive x-axis, then it is rotating in a clockwise direction. So, at the pitch point it is rotating in this way, and so the tangential force on the pinion will act in this direction. This is the direction of Wt, and that is the direction of positive z. So, in the direction of positive z, the tangential force on the pinion will be acting at the pitch point P. If I say this a pitch point P, then at this pitch point P, the Wt is acting in the positive z direction. Now, for the driven gear, that means this pinion is the driven gear. So, for the case of driven gear, the direction of Wt will be in the direction of rotation of the shaft. So, if this is considered as a driven gear, then it is rotating in this direction, clockwise direction, and so the tangential force on this, if it is a driven gear, will act in this direction, from this to this. But for our case, our pinion is driving member of the gear set, and so Wt will act in this direction, not in this direction. The direction of Wr, that means the radial force, always acts along the axis of rotation, and so it will act along this direction, along the direction of rotation. So, Wr for the case of pinion will act in this direction, and Wr for the case of gear will act in this direction towards the axis of rotation of the gear. Okay. We are not taking this in this problem because we were required to find the bearing reaction at A and B, which is the pinion shaft. Now, the axial force, determination of direction of axial force is very important. It is determined with the help of right hand rule. That means, if we take our right hand and these fingers are folded in the direction of rotation of that particular gear, then the thumb shows the direction of the axial force. So, in our case, the shaft of the pinion is rotating in a clockwise direction, the direction shown by these fingers, and so the axial force on the pinion will act in this direction. This is the negative x direction for the case of pinion shaft, and so the axial force will act in the negative x direction. Now, knowing the forces which are acting at this pitch point for the case of pinion, now we can draw the free body diagram of the pinion shaft A, B and this one. This is the axial force direction. This is the free body diagram of the shaft AB, from A to B, the distance is 250 mm. This is 250 mm, and from B to the pitch point is 75 mm, and this distance is the half of the pitch circle diameter of the pinion. That means dp pitch circle diameter of the pinion divided by 2. So, we have shown the forces which are acting at the pitch point C. The axial force is acting in the negative x direction, tangential force in the positive z direction, just we determined the direction, and the radial force along the axis of rotation of the shaft. Now, we have to show the reactions which will act at the bearing A and at the bearing B. The bearing A will take the thrust load, and so it will have an axial component also, that is taken as FAX, and the two other reactionary forces of the bearing are FAZ, the reaction in the Z direction, reaction in the Y direction. For the case of bearing B, it is only a radial bearing, it will not take the thrust load, and so there will not be any reaction in the direction of axis of the pinion shaft, it means the x. It has only component, reactionary component in the z direction and the y direction. So, with this free body diagram, now we will apply the static equilibrium equations. That means summation of all forces in the direction of x should be 0, summation of all forces in the direction of y should be 0, summation of all forces in the direction of z should be 0, and we can take the moment about the z axis, that should be 0, summation of all moments about the your z axis or the y axis should be 0. And you can also apply the summation of movement along the x direction should be 0, but the number of unknowns are 1, 2, 3, 4 and 5. And so, 5 equilibrium equations will be required to find the 5 unknowns. Now, one of the unknown you can determine easily, knowing that in the direction of x only 2 forces are acting, Fax and Wa. Wa is acting in the x direction. And so, when we will take the summation of forces in the direction of x is equal to 0, we will find Fax is equal to Wa, and that is 110.27 Newton. That means which is equal to Wa. So, Fa we have determined, and that is 110.27 Newton. Now, to determine other reactions, we are taking movement about z axis. That means summation of movement in the z direction should be 0. So, along the z we are taking the movement, and the forces which are acting other than z are Fyz and Fr in the direction of y and the Fa in the direction of x. So, they will provide the movement arm for the when we will take the movement about z axis. So, we got this 80.22, that means this Wr 80.22 multiplied by distance of A and this point, and which is equal to 250 plus 75, which is 325. And this is trying to rotate the system in a z axis in a clockwise direction. It is taken as negative. Then another component of force is this Wa, which is acting in the direction of x, and that will give the movement equal to Wa multiplied by this distance, which is dp divided by 2. So, that is obtained here. And it is trying to rotate the z axis in an anti-clockwise direction. So, it is taken as positive. Now, the third force which is acting other than z axis is this Fby. So, this will rotate this z axis, and the movement will equal to Fyb multiplied by this distance, and this distance is equal to 250. So, 250 multiplied by Fby should be 0. Solving this, we get the value of Fby. So, Fby is 95.12 Newton. Now, summing forces in the y direction gives Fay is equal to 14.9 Newton. Now, next, taking moment about y axis, that means summation of moment about y is equal to 0, provide us the value of Fbz. Fbz is equal to 249.3 Newton. Now, summation of forces in the direction of z is equal to 0 will provide you the Faz, this Faz, this, and this is equal to 57.3. Now, the next thing is the torque. Torque is equal to the transmitted force Wt multiplied by this dp divided by 2, and that is 3.97 Newton meter. You can solve this problem with applying the vector method also. So, in that case, what we do is we find the vector force vector at the C, which is Wc, and that is given by the 110.27, which is acting in the negative x direction. So, minus 110.27 I, and in the y direction, in the negative y direction, this Wr is acting. So, minus 80.22 J, and the transmitted force is acting in the positive z direction, and so 0.191 into 10 to the power 3 k is the force vector at W. So, combining this, we have a force vector WC. Similarly, we will have the force vector at B, force vector at A. The force vector, and we have to find the position vector of the B and the C. Position vector of B is given by 250I, and the position vector of C is given by 325. This x distance is 355j I, and 41 this dp divided by 2j along the y direction. So, then taking moment about this A and bifurcating the I, j and k components, we can find maximum of the forces. Then just apply summation of forces equal to 0. That means the force vector Fa, force vector Fb, and the force vector Fc should be 0, and then again separate the I component, j component and k component, you will get the forces. So, this is all about the first problem. Now, we are going to take the second problem, which is a design related problem. This problem is a 17-tooth 20-degree normal pitch angle helical pinion with a right hand helix angle. In the case of helical gear, the gears are inclined, and thus they will have either right hand or left hand inclination. Okay. So, the given is the right hand thread, right hand gear. 30-degree helix angle is 30-degree, rotates at 300 rps. When transmitting 3 kilowatt, the power which is to be transmitted is given, and the 52 teeth helical gear. So, number of teeth on the pinion is given, number of teeth on the gear is given, and the helix angle is given, RPS is given, power which you want to transmit is given, and the module is also given. This module is actually the normal module Mn, because it is a helical gear. So, Mn is 2.5 mm. The face width is 38 mm, and the set has a quality number of 6. So, the quality number, the way it will be mounted, the way it is made is also given. The gear are straddle mounted with bearings immediately adjacent. That means the orientation of bearing and the gear is given. It is a straddle mounted, means it is a simply supported type of arrangement, and the bearings are just adjacent to this. It means there will not be too much deflection of the shaft. It means mounting is very good. The pinion and gear are made from a through hardened steel with surface and core hardnesses of 240 Brinell. That means pinion and gear both are through hardened. It means there is no any separate hardness for the core and the case. This is the case and this is the core. There is no separate hardness, but throughout the gear tooth or throughout the gear, it is hardened by a similar Brinell number. The gear is hardened 240 Brinell and the pinion is hardened 200 Brinell. The transmission is smooth, connecting an electric motor and an centrifugal form. This information is very important. This will give you the overload factor for the bending stress and the contact stress which acts on the gear. Assume a pinion life of 10 to the power 8 number of cycle. Life of the pinion is given and the required reliability is 0.9. Use the upper curves in the life factor. These all information we will take while designing the gear. Now, the question is, find the factors of safety of the gears in bending, then find the factors of safety of the gears in wear. Then by examining the factor of safety, identify the threat to each gear and to the mesh. So, these values are given. Number of teeth on the pinion 17, pressure angle phi n is 20 degree, RPS of the your pinion is 30, is 30, and the power which you want to transmit is 3.0 kilowatt. It is given here. Then the number of teeth on the gear ZG is 52, and the face width is 38. Face width is given as 38, and the quality value is 6. Quality value is 6. Then the normal module is 2.5. Helical gears are defined by normal module. Helix angle is 30 degree. Pinion material is grade 1 steel through hardened to 240 BHN, and the gear is also grade 1 steel through hardened 200 BHN. Life is 10 to the power 8 cycles and reliability is 0.9. So, with this data, let us start the designing of the helical gear. These are some things. As we studied in the first problem, helical gears, the teeth are inclined, and we take the section of the gear teeth in the normal plane and in the transverse plane. Then we have the normal pressure angle and the transverse pressure angle. Similarly, we have a module MT and MN. And the relationship between MT, the transverse module, and the normal module is MT is equal to Mn divided by cos of the psi, where psi is the helix angle, which is the angle between a line which is tangent to the gear tooth and a line parallel to the axis of rotation. So, this angle is your psi. So, MT has come as 2.88 mm. Knowing the MT, now we can find the pitch circle diameter of the pinion and gear, because number of teeth on the pinion and gear are given. Number of teeth on the pinion is 17. So, 17 multiplied by MT is the pitch circle diameter of the pinion, and number of teeth on the gear is 52. So, 52 multiplied by MT, the transverse module, is equal to the pitch circle diameter of the gear. Then the gear ratio mg is equal to the number of teeth on the gear divided by number of teeth on the pinion, and so it is 52 divided by 17, 3.06 mg. Now, transverse pressure angle is 22.796 from this relationship, tan inverse tan of the phi n divided by cos of the psi. We have phi n as 20 degree and psi as 30 degree, and so phi t is equal to this one. Then the radii of pinion and gear are just half of the pitch circle diameters. Then the base circle or radius of pinion and gear, the relationship between base circle radius and pitch circle radius is, the base circle radius is equal to pitch circle radius and cos of the phi. Okay. So, in this case, we have the base circle radius of the pinion is equal to the pitch circle radius of the pinion multiplied by cos of the phi t. In the case of helical gear, we are not taking the normal module to determine the pitch circle diameter and the base circle diameter. We are using the transverse module. That means the direction in which the gear was in the transverse direction along the AA section. Whatever MT we are getting, this will give you the pitch circle diameter and the base circle diameter. So, base circle radius of the pinion is 22.62 and base circle radius of the gear is equal to 69.22. We know that base circle is the circle from where involute tooth profile is generated. Then the tangential pressure angle obtained is 22.796 degree, and the pitch circle radiuses are given by this and this. For the case of pinion and gear, we have just obtained it. Similarly, the base circle radiuses are this one and this one. Then the contact ratio is equal to LAB divided by RB cos phi. What is the LAB? This A and B are the start of engagement and end of engagement. So, this length between A and B is called the LAB, which is the contact length, divided by base circle radius cos of the phi t is called the contact ratio, and contact ratio provides us the average number of gear tooth which are in contact, and there is a load sharing. So, knowing the value, this LAB is equal to RG, base circle radius of the gear, plus addendum. Standard addendum is equal to 1 module, and standard dedendum is equal to 1.25 module. And addendum and dedendum, as we all know, is equal to, if this is your pitch circle and this is your addendum circle. So, above the pitch circle, the height of the gear tooth is addendum, and below it is dedendum B. So, knowing the value of A and the pitch circle radiuses, we can find the length of contact LAB, and that is obtained as this one. Now, after determining the parameters of the gears which we are going to design, now let us find how to design a gear in a mesh. A useful decision set for helical gears include some a priori decisions we have to take, and that are load which you want to transmit, that means the transmitted load WT, and this WT we obtain from the power which you want to transmit, and the pitch line velocity or pitch circle velocity V gives us the WT. So, the load and the speed, reliability, life and the overload. Then the factor of safety, then the tooth system. The tooth system consists of the normal pressure angle, helix angle, addendum, dedendum and the root fillet radius. Root fillet radius means at the root there will be a fillet like that. So, what is the root fillet radius? That we have to make a priori decision. Then the gear ratio ZG from the ZP and ZG, number of teeth on the pinion, number of teeth on the gear. Based on these a priori decisions, we take decision on the quality number, what should be the quality number of the gear, then the normal module, face width, pinion material, its core hardness and case hardness, gear material, its core hardness and case hardness. Now, if we inspect our problem, the given problem, then these everything are given to us except the factor of safety, this. So, with all these datas, our aim is to determine the factor of safety. The general steps after a priori decisions have been made are choose a, this is the general procedure, this is not based on this particular problem. So, if in general case module is not known to us, so from this table we choose a module and we start solving our problem, and if we are not getting satisfactory result, then we again come back and select another module, either a smaller one or the bigger one based on our final outcome. Then examine implication on, after taking this module, we will find the other parameters of the gear and we will check whether we are getting satisfactory result or not. If not, then again we will come back and go and take another decision. It means the design is not a serial problem, it is a iterative process. We have to come back, take another decision and then start making the process, and if satisfactory result are not still coming, then again we come back and take another decision. So, that all is given here. We know that in the case of helical gear, two types of stresses acts. First is the bending stress at the root, and at the point of contact the Hertzian contact stresses, and therefore it may fail due to fluctuating bending stresses, at these location and surface fatigue at this location. So, we have to find this bending stress and the surface stress, and they will be checked with the bending fatigue strength SFB and the surface fatigue strength SFC. And the stresses which we will be determined is sigma B, the bending stress, and the surface stress sigma C. And this will be done for both pinion and gear, and thus we will get two values of this sigma B and SFB, sigma B of the pinion, sigma B of the gear, and similarly SFB for the pinion and gear, sigma C for the pinion and gear, SFC for pinion and gear. And with the help of that, we will find the factor of safeties, and that is SFB divided by sigma B. This is for the bending, and for the contact stresses, NC will be SFC divided by sigma C. And we will check whether we are getting satisfactory factor of safety or not. So, let us see how we are dealing with this. These are the design objectives. We have to take care of the bearings which are used to transmit the power, to support the shaft, then the housing, and the driver and driven machine. So, in bending, the bending stress equation is equal to WT FMT JP. MT is the transverse module, JP is the geometry factor for the case of pinion, geometry factor for the case of gear. Then these are the modifying factors of the WT, transmitted load, due to various reasons: the velocity factor, overload factor, the mounting factor or the load distribution factor, size factor, then the rim thickness factor and the idler factor. Then the strength of the material against bending fatigue, it is given by from the AGMA materials data, we get bending fatigue stress strength as SFB dash. It is corrected by the life required, temperature required, and the reliability required. So, and then factor of safeties are determined, and the factor of safety against bending for the case of pinion is equal to the strength, bending fatigue strength of the pinion, and the bending stress which is acting on the pinion, and similarly for the case of gear. And for the contact stresses, the contact stress equations are like this. This is equal to elastic constant Cp. This is geometry factor for the pitting resistance, and these all factors are very much same as were used for the case of bending stress. The strength of the material against pitting resistance or surface fatigue is for the pinion. This strength is obtained from the AGMA materials data, and this is the life correction factor, temperature correction factor, and the reliability correction factor. Because this SFC dash is for 10 to the power 7 number of cycle, reliability equal to 0.99, and temperature less than 120 degrees centigrade. So, if any of these is other than your required life, temperature, and reliability is other than this, then you have to use these factors. Factor of safety against contact stress is given by this for the pinion and this for the case of gear. Now, let us find one by one the factors. The overload factor, in the problem it is given that the driving machinery and driven machinery are uniform, and so KO is equal to 1. If it is other than this, then it will help you like this. That means, if the source of power, that means the power to which pinion is connected is of medium shock, and the machinery which you are driving is of heavy shock type, then KO would have 2.25. But as in our case it is uniform, then it is 1. Given that transmission is smooth, connecting an electric motor and centrifugal pump, and so KO is equal to 1. Now, the geometry factor is determined for the bending stress. Geometry factor is this one. For the case of pinion, it is JP. For the case of gear, it is JG. And J dash is given by this formula, J, the geometry factor, where Mn is the load sharing ratio, which is equal to Pn divided by 0.95 LAB, the length of contact which we had determined some time back. So, the value of y dot is modified Lewis form factor and LAB are found in the AGMA standards. So, for the case of helical gear, the geometry factor J is determined with the help of figure A and B given in the coming slides. From the figure A, we get the value of J dash corresponding to the helix angle of our gear and the number of teeth on the gear. And this figure is applicable when the number of teeth on the mating gear is 75. If number of teeth in the mating gear is other than 75, as in our case, the pinion is having 17 number of teeth and the gear has 52 number of teeth. So, they are not messing with 75 number of teeth, and so this J is not actual J, it is J dash. And to get the actual value of J, this J dash should be multiplied by a modifying factor, and that is obtained with the help of figure B. So, how we will determine it? For our case, as we know that the ZP is 17 and ZG is 52, ZG is 52, psi is 20 degree, and therefore, we obtain J dash as 4.5, J dash as 4.5 for the pinion and J dash for the gear it is 0.54. The modifying factor, because the mating number of teeth on the mating gear is not equal to 75, so we have to use the modifying factor. Knowing the ZP as 17 and ZG is equal to 52 and the helix angle is 20 degree, and so from the 20 degree we will find a line corresponding to the number of teeth in the mating element. So, for the pinion, we have to extrapolate to get the value of kV for number of teeth equal to 17 to get the value of this modifying factor, and that is shown here. This red color is for the pinion and green color is for the gear, and the modifying factor is obtained as 0.94 and 0.98. So, geometry factor for the pinion is J dash multiplying by modifying factor is given by this one, and J of the gear is J dash and the modifying factor is 0.529. This can also be obtained with the help of this AGMA table, where on the first column is the gear teeth. The gear teeth for our case is 52 and 52 is not here, and so we have to interpolate the values. And the number of teeth on the pinion is 17, and so if somewhere is 52, so corresponding to the 52, we will get the J for the pinion and J for the gear. And by interpolation, we got JP as 0.429 and JG as 0.29. Now, the dynamic factor, the original equation of bending stress was derived considering the static case, but it is not the case of static. The gears are moving or rotating and there will be the dynamic effect. And so, the dynamic effect is either obtained from this Bath equation or from the AGMA equation knowing the quality number. And the quality number from 3 to 7 is for most commercially quality gears, and in our problem the quality number of 6 was given, and it means it is the commercial quality gear. If it is not given, then depending on what type of your gear is, you have to select the quality number. Quality number 8 to 12 are of the precision quality. So, knowing the quality value, we will get the value of this kV velocity factor. Knowing this A and B, B is in terms of quality value. So, value of A and B are substituted to get the value of kV in meter per second. This figure can also be used knowing the pitch line velocity and the quality value. So, if the pitch line velocity is letter 10 and the quality value is 6, then the kV is 1.6. But we are going to use the formula. So, we will have this pitch line velocity and this Wt is equal to 649. So, quality value is 6. So, in the equation of B, 6 is substituted, and then the A is obtained from this one, substituting the value of B, here, we get the value of A, and then dynamic factor Kv is obtained as 1.404. Then the next one is the load distribution factor Km, this Km of the bending equation, and this Km will be same for the case of pinion and gear. The procedure is applicable to these cases, and the Km consists of the following factors, and these factors are determined in these slides. The first of all, this CMC is equal to 1 or 0.8 depending on whether the teeth is crowned or uncrowned. In our case, the teeth is not like this, we are not taking crowned, and so our teeth is uncrowned, and so CMC is 1, CMC is equal to 1. Similarly, the next factor CPF is determined. Knowing the value of face width and the pitch circle diameter, we get F divided by 10 dp. First of all, this is determined. If it is less than 0.05, then we take F divided by 10 dp is equal to 0.05. But in our case, substituting the value of face width and pitch circle diameter, we got it as 0.0774, and thus it is more than this 0.05, and so based on the face width, we will use this formula. Our face width is 38, which is within this range, and therefore we will use this formula to get the value of CPF, and which is equal to this one. Then the next one is CPM. CPM is either 1 or 1.1 depending on whether it is straddle mounted pinion. In our problem, it was given that the bearing are straddle mounted and they are just adjacent to the bearing. It means this S1 is bigger, and so our case is straddle mounted pinion with S1 divided by S less than 0.015. Considering this case, our CPM is 1. So then the next factor is CE. CE is 0.8 or 1. 1 is for other type of cases, and the 0.8 is for the compatibility is improved by lapping or both. We are not certain about this, it is not given in the problem, and so we have taken this one, and it is 1. Then finally, the CMA is obtained with help of this formula, and considering that we have a commercial enclosed unit, getting the value of A, B and C, substituting in this, we get the value of CMA. So after getting all the factors, substituting this in this equation, the Km is obtained as 1.206. Then the next one is the size factor. The size factor has this equation, which is a function of face width, module, and the Lewis form factor, the original Lewis form factor, which is determined from number of teeth. So for the case of pinion, number of teeth is 17, and so the Y is equal to 0.303. For the case of gear, it is 52, and so these two values will be interpolated to get the value of Y. So substituting all these, the value of size factor for the pinion, size factor of gear was obtained. Then the rim thickness factor. Our case is not based on the rim, or if it is on the rim, then what we do is the rim thickness is made bigger so that the ratio of rim thickness to the total height of the gear, that means addendum plus dedendum, should be greater than or equal to 1.2, and thus Kb is equal to 1. We have taken this condition, and so Kb is taken as 1. And we will ensure that if the gear is made by a rim type of arrangement, then rim thickness should be more than 16.2 mm. Our gear is not an idler. For if it is idler, then idler factor of 1.42 is taken. Our is not an idler, so Ki is equal to 1. Knowing all these factors, now we can find the bending stress because we have all the factors. Similarly, for contact stress can be determined, but only two factors we have to find, Cp and this I. So let us find these two factors. Cp is given by this table. Our case is a steel and steel, and so the Cp is equal to 191. Depending on the material of pinion, material of the gear, we have to take the value of Cp. Then the I is determined from this formula, which is sin phi t cos phi t divided by 2 mn mg divided by mg plus 1. So, we have all these values. We can find the this mn is equal to Pn divided by 0.95 LAB, and Pn is equal to the normal pitch cos of the normal pressure angle, and normal pitch is equal to pi multiplied by normal module. Substituting this, we get the value of this Pn, and thus we will have this Mn. Mn is equal to 0.678, and thus substituting the value of Mn Mg in the equation of I, we get the value of I as 0.198. And thus we have determined the bending stresses and contact stresses which will act on the pinion and the gear. Then determination of strength of the material against bending. So, this we have to determine first, and this is determined from the AGMA materials data, and in the problem it is given that both pinion and gear are through hardened. The reliability factor is determined in the equation of your SFB is equal to CL or simple KL divided by KT and KR reliability and SFB dash. So, this Kr is the reliability factor because this SFB is based on 0.99 reliability, but we are going to design our gear for reliability 0.95, and so we have to use this Kr. If reliability would have 0.99%, then reliability factor would have 1, but as it is other than 0.99, lesser than that, and so it is 0.88. So, reliability is 90%. Then the life factor is determined with the help of this figure, and in the equation it was given, in the problem it was given that upper curve is to be used. So, this upper curve corresponding to 10 to the power 8 number of cycles, 10 to the power 8 number of cycles, this upper curve will give you the value of KL, and so KL has this formula. So, we have used the formula. In place of n we have substituted the 10 to the power 8 number of cycle for the pinion, and for the gear the life of the gear will equal to life of the pinion, which is 10 to the power 8 divided by gear ratio mg, which is equal to 4. So, life factor is determined. Then the material datas are given. This table is for nitriding gear, what should be the case and core hardness. For our case and core hardness through hardened gears are there, and for the pinion the hardness is 240, and for the gear it is 200. And so, we are directly coming to the case of steel. For the case of steel, these two curves are there. On the x-axis is Brinell hardness number, and the y-axis is the SFB dash. So, depending on the hardness given, we can find the strength. But we are going to use this formula for the grade 1 material, and that formula provides the SFB dash for the pinion. In this formula, in place of HB 240, which is the Brinell hardness of the material of the pinion. Similarly, Brinell hardness of the material of the gear is 200. So, by substituting these values, we got the value of surface fatigue strength of the pinion and gear. These are other datas. Depending on the type of material, you can choose the strength or these equations. Now, the surface fatigue strength is determined in a similar way. For the steel, these two curves can be used, and for the grade 1, we have this formula. Substituting the value of Brinell hardness, we will get the 240, we will get the surface fatigue strength of the pinion and surface fatigue strength of the gear. Now, we have to find this life correction factor for the pinion and gear. SFC dash we have determined. So, this is again determined with the help of this figure, and the life required for the pinion is 10 to the power 8, and so this will give you the value of CL for the pinion. But we are going to use directly this formula, and using this formula, substituting the life required for the pinion and life required for the gear, which is equal to life of the pinion divided by mg, we get the CL of the pinion, CL of the gear. Okay. Then the hardness correction factor or the hardness ratio factor, which is used only for the case of gear. This is determined with the help of this formula, CH is equal to 1 plus A dash mg minus 1, where A is this one, which depends on what is the ratio of Brinell hardness of the pinion, Brinell hardness of the gear. So, this is the case. For our case, it is 1.2. So, A dash is given by this equation. Substituting the value of HB divided by HB of the pinion, HB of the gear, we get A dash. Substituting A dash, we get the CH for the gear in this equation. The mg is, the gear ratio is 3.06, and so it is the hardness correction factor. This is applied only to the gear. Now, the bending stress on the pinion tooth, after knowing all the factors, this MT, F, WT, we can find the bending stress on the pinion, which is 24.78. And the bending fatigue strength, we had determined this SFB dash, and the life factor, temperature factor will be 1 because temperature is less than 120 degrees centigrade, and this Kr reliability factor we have determined. So, corrected surface bending fatigue strength for the pinion is this one, and so the factor of safety of the pinion against bending fatigue is this SFB, this divided by this, and so it is 10.25, too much high. Similarly, bending stress on the gear tooth is determined, and the factor of safety of the pinion against bending stress is 11.7. For the surface stress for the pinion, this equation will give you the value of surface fatigue stress, and this is giving you, after substituting all the factors and this SFC dash, which is 733, we got this one. And so, the factor of safety of the pinion against contact stress is 2.75, this divided by this. Similarly, for the gear, the surface stress and the surface fatigue strength is obtained, and the factor of safety is of the gear against contact stress is this divided by this. Finally, we have factor of safety of the pinion against bending is 10.25, factor of safety of the gear against bending 11.7, so factor of safety of the pinion against contact stress, and factor of safety of the gear against contact stress. For comparison purpose, what we do is, this is directly related to under root of the WT. This is also related to under root of the WT. So, these should be squared to compare it with these factor of safeties, because they are related to WT. Sigma B is equal to WT, like that, other factors, and sigma C is CP and under root of the WT. Okay. So, for comparison of the pinion, we have taken NC square, and NB, which is 10.25, is compared with NC square, which is 2.75 to the power 2 or square, that is 7.56. So, what we are getting is, if we are comparing the factor of safety of the pinion against bending and factor of safety of the pinion against contact stress, then this 10.25 should be compared with the 2.75 square, and that is 7.56. So, factor of safety of the pinion against contact stress is lesser than the factor of safety of the pinion against bending. It means the pinion is under threat in wear. So, we have to check the pinion for its life. And we may see also that the factor of safeties are very bigger. So, we can either change the material, we can either change its hardness, or we can change the module, so that the factor of safety are within limit of 2. So, for the gear, this is the case. NB of the gear is compared with NC gear square, and so 11.7 is compared with 6.5. So, gear is also under threat in wear. These are the references which were used in this tutorial. So, in this lecture, we studied 2 problems. The first problem was related to different parameters of the helical gear. That means its tangential pressure angle, the normal pressure angle, and the helix angle. And thereafter, we determined the forces which are transmitted, that means WT, and the axial force WA, and the radial force WR. And then we found the bearing reactions. In the second problem, we took a design problem, and we found that by comparing the factor of safeties, the pinion and gear are under threat of wear. Thank you.